My name is Nathan Rake, Manager of State and Local Affairs. Before we dive in with our amazing panel this evening, I want to walk through some brief background information about battery storage. Renew Northeast is a nonprofit member organization advocating for over the past 17 years for the responsible and reliable development of clean energy in New England. Renew is unique in that we are governed by a coalition of the leading developers of clean energy and environmental organizations, such as the Conservation Law Foundation, Union of Concerned Scientists, and the Nature Conservancy. Together, this allows Renew to provide a single, coherent voice to achieve clean energy policy goals. The New England grid is undergoing rapid change. We are transitioning from an energy grid that was primarily fueled by coal and oil to one that values a diverse range of resources, including a greater penetration of renewable resources. This change is primarily the result of state clean energy and decarbonization goals, which increases the total demand on the grid. As a result, demand in New England is forecasted to grow by 2 to 3 times current levels by 2050. For context, the current New England grid operates on a 15,000 megawatt system. In order to address this forecasted rise, state policymakers and regulators have prioritized dozens of pieces of public policy addressing topics ranging from renewable integration, grid reliability, and affordability. Together, as part of this transition, at least 6 transmission upgrade projects have been proposed that have the potential to deliver upwards of 10,000 megawatts of clean energy to New England load centers. Battery storage plays a pivotal role in the evolving New England grid. BESS supports the integration of more renewables, such as solar and offshore wind, by storing the extra energy for later use. This energy can be used to help balance demand on the grid for times when the sun isn't shining or the wind isn't blowing. This provides ratepayers with access to least cost and cost-effective energy. For example, batteries can help time shift demand, enabling other energy resources to be used as they become available or are more cost efficient. Also, when batteries are deployed at periods of peak demand, this can help dampen price volatility and stabilizes wholesale energy markets. Finally, storage can reduce the reliance on fossil peaker plants, which are costly and can have negative impacts on health. To that end, Massachusetts is actively working to procure battery storage. Beginning in July, DOER and the electric distribution companies issued the first RFP for energy storage under Section 83E. In this first RFP, the EDCs are looking to procure 1,500 megawatts of energy storage and will procure a total of 5,000 megawatts by 2030. Successful bids in the first RFP are expected in early December. What does this mean for you? Renew is building a network of community leaders who are interested in ensuring that local voices are part of the dialogue around our clean energy future. We recognize that communities have a lot on the line and that communities may have many questions. Renew wants to share our resources and knowledge to amplify local perspectives. Consider joining our mailing list to get timely updates on pending public policy changes and issues that are relevant to you. Now, before I introduce our moderator for this evening, some quick housekeeping items. Please use the Q&A icon to share any questions with our panelists. The chat feature is disabled for this webinar. Now, it is my pleasure to introduce our moderator for this evening, Dave Wilby. Dave, would you like to say a quick opening word?
Thanks, Nathan. So good evening, everybody. I'm Dave Wilby. I am with Wilby Public Affairs, where I have a consulting practice where I provide strategic public affairs services to energy developers and operators across New England, and including a lot of work on energy storage. So very happy to join everybody this evening, including our talented and knowledgeable panel here. Our objective tonight is to bring a few experts together to discuss battery storage, answer some questions, and hopefully inform you all about some key aspects of this topic. Given the time and scope of this subject, we're not likely to get to everything, but we'll do our best to provide you with useful information. And I know our audience includes both storage experts and those new to the subject. So we're going to aim to not leave anybody behind tonight by getting too deep into the weeds or over-reliant on acronyms. But again, feel free to submit a question at any time through the Q&A function. We'll get to many as we can. One other note too is battery storage and energy storage can take many forms and many scales. We're going to talk a bit more about somewhat the larger end of the spectrum. So if you have questions about the battery on your scooter, we may not be the folks to ask about that. So after the panelists introduce themselves and make some brief introductory comments, we'll start with a round of questions from me. Then as questions come in from you all, those will be brought into the conversation. So as I mentioned, we've got a broad range of perspectives assembled tonight as this group brings knowledge about how storage integrates with the electricity market and the grid, expertise about the safe deployment and operation of battery storage, and firsthand real-world experience operating battery storage in a municipal electric utility system. So let's get to it. So with that, I'll turn it over to our first panelist to say hello, Abby Sherman.
Good evening, everyone. I'm Abby Sherman. I am the manager of electricity markets at the American Clean Power Association. I focus on transmission expansion and market policies in the wholesale regional electricity markets, as well as grid reliability topics, including inverter-based resource reliability standards. I'm coming from a regional grid operator perspective, and we'll be speaking to grid-scale battery storage facilities and some of the more technical points on the topic for this evening, really highlighting the reliability and affordability benefits of battery storage systems. We as an industry want to see policy that creates business certainty and a pathway for responsible and safe development, and we want to work with states and the grid operators to see that happen. Thank you for having me. It's great to be here.
Thanks, Abby. I think we'll turn to Peter Dion next. Peter?
Good evening. My name is Pete Dion. I'm the general manager of the Wakefield Municipal Gas and Light Department. We installed our first utility scale battery in 2018 as part of a peak management program that we had. And since then, we have embarked on a larger project now that has a dual purpose. And it was shown in the picture that Nathan had earlier, the Energy Park, which is a dual purpose battery and generator site that to provide emergency backup to two high schools that are under construction in Wakefield, the Wakefield Memorial High School and the Northeast Regional Technical School. And so the battery is going to serve as the emergency backup, eliminating the need for two generators at those schools. And in addition, it'll serve as a peak resource. Because of that project, we are also evaluating a third 5 megawatt, 15 megawatt hour battery for the other side of our town for additional peak and resilience. I'm proud to be here. Thank you.
Thanks, Pete. Nick Warner.
Everybody, thanks for having me. I am Nick Warner. I'm the co-founder and managing principal of Energy Safety Response Group. We help our customers design and build safer batteries. We test and certify those batteries. We educate stakeholders, much like those of you on this webinar, about the myths and realities of energy storage safety, help permit those systems, and then support emergency response through planning, training, and acting as the emergency responders ourselves if something were to ever happen. We don't just believe that energy storage could be done safely in the future. We know energy storage can be done safely today, and we help people like those on this call do energy storage safely around North America.
Thanks, Nick. So let's get this conversation started, and I'll pose the first question. and really pick up on a theme that Pete touched on briefly, but that is how battery storage can improve reliability. And I think we'll turn to Pete to talk about the experience they've had in Wakefield and what they expect going forward as they get further storage up and running. And then maybe Abby can chime in a bit too on sort of the broader perspective. Pete, you wanna tackle that?
When we installed our first battery in 2018, it was as a peak management resource for Wakefield. The cost benefit analysis on that said we would get a payback in about 3 to 5 years, and we paid it off within the first 3 years based on the value we had on deferring our capacity requirements. Since then, as I mentioned, we're a gas utility as well. And we had 2 large high schools being built in Wakefield at the same time. And we really did not want to add either of those schools to our gas system. So we needed to find a way to convince them to go all electric. And because of that, we needed to come up with a creative use of our resources, driven mainly by the battery, where we've actually installed the battery between the 2 schools, and that is acting as the emergency supply to both high schools. So they don't require diesel fire generators, and we did have to add a natural gas generator in addition for if there is a long-term outage. But one of the key pieces of this project is that we can run it as a true microgrid and isolate completely from the system, and actually serve as a heating and cooling center for the town of Wakefield at the new high school. So there were multiple purposes for this project. And in this case, it wasn't just peak management, but it was also an advanced applications that can serve that the battery can serve.
So Pete, just to probe a little further, so can you just mention where you mentioned the 2 schools and the battery will serve as a backup? This is all within essentially one campus. They're all kind of closely connected.
Yeah, very closely connected. The 2 schools are about a quarter mile apart, and we built the energy park in the middle between the 2. So we're connecting to both schools. They're off the same road. So we have the opportunity in this location to kind of demonstrate and utilize a lot of things. As part of the project, we also are putting solar on both roofs, so that will be connected to the microgrid as well. So it's a multi-layered project, and so the excess solar will also help to charge the battery when the schools are not using it. So it was a multifaceted program. Part of the reason we did this was, again, to encourage them not to go on gas, but also we needed to provide some financial incentive to them. So each school was able to save about $1.4 million in construction costs by not having to install a diesel fire generator. So that's almost $2.8 million in savings between the 2 schools. And then installing the solar on the roof right at the start of the project, rather than it just being quote unquote solar ready, had another huge impact on the project cost benefit analysis for the 2 schools.
Terrific. Thank you. That's a great example. Abby, do you want to sort of maybe zoom out a little bit and give us a kind of a broader sense of how storage can play a role in grid reliability and resilience?
Yeah, so zooming out, looking at the, kind of larger electrical grid and kind of bringing this more technical perspective, power demand and supply must be balanced at all times on the system, and batteries help maintain this balance and ensure that the frequency, which I think is a simple way to think about it, is electrical rhythm, remains consistent and stable. Batteries are also able to stabilize frequency after a disturbance, apart from, maintaining it on a consistent basis, which is, for example, when a large generator trips offline. Batteries help maintain proper voltage levels across the grid and quickly restore stability following a disturbance. And I think voltage is, a simple way to think about that is electrical pressure. And when there is a complete blackout, batteries can start the grid back up very quickly, which is what we call black start capability. And I think the last point is that resource adequacy that's not a simple term, but is essentially the grid's ability to meet electricity demand at all times, even during disturbances such as an extreme weather event. We'll get more into this part maybe in later questions, but since batteries are able to store power and release it when it's needed, they serve as sort of a reservoir when we see other generators suddenly tripping offline during these disturbances. So all of those, factors combined really help maintain, a steady state of supply and the overall stability of the grid when you're looking at voltage and frequency.
Thanks, Abby. So let's turn to safety. Nick, you help clients deploy and operate energy projects safely all over the map, not just in our region. I think the question for you is, do you encounter in your travels, are there common misconceptions about battery storage safety? And if there are, maybe you could set the record straight for us about some of them.
Yeah, absolutely. I think first and foremost, people assume it's a foregone conclusion that energy storage systems are going to catch on fire when they're in their community. It's not oh, you can't put that there. There's a 1 in 50,000 chance it may catch on fire. It's oh, that thing's going to burn every year. And that's simply not true. There are tens of thousands of energy storage systems deployed around hundreds of projects just around the US, significantly more around the world. And the failure rate of these systems has been incredibly low. In fact, there's a database online where you can look not just at fires internationally, but within the US. A number that we've been using recently is that in 2022, according to the National Fire Administration, there were 12,800 electrical or equipment fires in a commercial and industrial setting. There were 4 stationary energy storage fires that were reported. So the failure rate of these systems is low. Unfortunately, they get a tremendous amount of media attention when they do, as is the nature of the media. And along with that, there's unfortunately been a lot of misreporting and misinformation that goes with it. There's an assumption that the batteries pose a significantly greater toxicity risk than any other than in other similar fires, and it's simply not true. In fact, we actually have more data now on what comes out of energy storage system fires than we do a lot of other things in the built environment. We're rushing to catch up on the emissions from the built environment, but whether you're looking at electric vehicles versus internal combustion engine vehicles, or looking at stationary energy storage systems compared to commercial, industrial, or even residential structures, they're really made of a lot of the same stuff. The batteries are a little bit different, and so you may have some metal particulate or things like that that may be involved, but generally the batteries are a lot smaller than other things that burn, and ultimately all fires pose health hazards if you're downwind. So the same common sense applies whether you're in the fire service and need to wear PPE and proper SCBA regardless of the fire, or if you happen to be downwind. Communicate and coordinate with the fire service. They're going to be monitoring the situation. They'll make decisions about what the community needs to do based on the reality on the ground, not some automatic assumption that the batteries pose some significant environmental risk. So we've got a tremendous amount of data both from the lab and from the field that backs this up there, with the exception of one very large incident in California with a globally unique system that'll never exist again. There's never been a reported health impact off-site from an energy storage system in North America, and we look forward to keeping that record going.
Thanks, Nick. And any reaction to the following, which is my sense is that those who develop and own battery storage projects have an enormous incentive to put safety paramount in their considerations, because if there's a problem, their investment is imperiled. How do you find clients thinking that through?
Yeah, so at the end of the day, people are deploying energy storage because it benefits the grid. It provides the resiliency and the positive impacts that we just discussed. But in doing so, they generate capital, they generate revenue, they generate money from this. So if I have an asset that's been damaged or destroyed, ultimately if you want to look at this, maybe negatively or, with a jaded lens, it comes down to money. And an asset that's been destroyed by fire because you cut corners with safety is not generating revenue. But more than that, when there is an incident, it tends to take the whole site offline for a significant amount of time, which means that payback that Peter talked about and that ability to support the grid isn't there. So I've been involved with code development going back almost 9 years now. When it first started, in that time, we've made tremendous gains and really matured the fire code in terms of staying with the industry. We've done something similar with product standards. So, you made the comment about micromobility earlier. Stationary energy storage systems like we're discussing here aren't just more regulated than micromobility devices, they're significantly more regulated than electric vehicles as well. In fact, it's almost unfair to say they're more regulated because the reality is, they're exponentially more regulated, orders of magnitude greater regulation for these batteries in terms of product standards, fire code requirements, as well as local requirements in some cases to install these systems. There's significant testing, millions of dollars of testing now is required for each of these systems before they're installed. We've got a really robust regulatory framework, both from the utility side and the fire code side, to ensure that they go in safely. And the New England area has been a leader in adopting and developing a lot of that code too.
And if I could just tag what Nick is saying, we've had the ability to, we had the experience of starting with a battery in 2018, but partnering with local police and fire is critical. The design of the systems has changed. They're much more modular now, as Nick was saying, but also the relationship that we have with police and fire. We have the experience of having 8 years under our belt on a prior project. So when we shared the new project with the police and fire, they appreciated where we had been, and they also appreciated how far the design has come in the new systems as well. So it's been a lot easier to have a partnership with the community because of that.
Yeah, part of the requirements in the fire code are to have a thorough emergency response plan, and every iteration of the code we're further defining what needs to be in those emergency response plans. Likewise, there's requirements for training for the fire service. So there's no excuse for a system to be installed without thorough emergency planning and training for the fire service, as well as 24/7 support for them if they have questions.
Terrific. Thanks, guys. So let's move back maybe more to how these facilities operate. And for grid connected battery storage, right, you've got a block of stored energy. So the question is, how do utilities and the grid operator in our region, ISO New England, how do they coordinate? How do they interface with the battery storage project to manage that power, how to deploy it during peak periods of peak demand? Abby, you want to maybe jump in, and then Pete, your experience perhaps as well after that?
Yeah. So, the function that batteries are used to manage peak demand and then also to integrate renewables kind of go hand in hand. So grid operators and utilities use batteries for what we call peak shaving, which I think Pete mentioned a little bit, which is storing excess electrons. You're charging when demand is low, and then discharging when demand is high to shave off the top of that demand curve. Further, when there's a lot of activity on the grid, there can be a strain on transmission lines, which is what we call, congestion, similar to rush hour traffic. So, batteries can be installed at certain points where we do see a lot of this congestion on the grid to help, reduce the strain on these transmission lines, kind of similar to opening up an extra lane on the highway. You're not necessarily adding more, you're just providing another place for those electrons to go. And so, batteries will charge during the highest solar output hours during the day when demand is typically lower, and discharge during those high demand periods, typically in the early evening when, folks are coming home from work and school. Similarly, wind output is usually highest overnight. So batteries will charge when that wind output is high and demand is much lower, and then discharge come early morning when folks are waking up to get ready for school and work, and those things. So, you know, batteries, this is getting a little bit into the weeds, but they can commit to becoming available during critical peak periods, you know, which, going back to the piece I just mentioned, helps during those times where the wind is not blowing, the sun is not shining.
Pete, anything to add from your perspective as a
Sure.
utility manager?
Yes, so our batteries are connected on the other side of the meter, but we're still contributing in the same way. We're monitoring the peaks on the system. The way we generate financial benefit is by curbing our own internal capacity requirement. So it's very similar. So we're monitoring the system peak because we only get savings if we run when the system is peaking and we take that load offline for them. So our first battery is a 3 megawatt, 5 megawatt hour battery. It was, you know, relatively small. Our new battery is a 5 megawatt, 15 megawatt hour battery. The key to operating both of those is understanding when the peak is going to hit and what buffer we have around that time frame so that we're making sure we're hitting the peak time. And so do we run it for a very short time at a high level of output, or do we spread that out over 3 or 4 hours? And it depends on the situation and the timing. Is there a temporary peak, or is there an overall you know, evening peak between the hours of 4 and 7, say? So we design our output of the batteries based on what we're forecasting for the peak. We have a regional entity named MWEC, Massachusetts Municipal Wholesale Electric Company, and they have a resource as part of that service that monitors the peaks from ISO New England, and we use them to help dispatch the batteries that we use. And there's I think there's 8 or 10 other municipal electric departments that also have batteries. So MWEC can dispatch all of those at the same time and serve as a capacity resource overall. But it's critical to understand the timing window so that you actually get the most benefit out of it.
Thanks to you both. Let me ask just a basic sort of understanding about how batteries work in terms of the power they can deliver. So, and I'll, Abby or Pete, if you want to address this, but if you have, let's say, a 4-hour duration, 20 megawatt battery system, you can deliver that 20 megawatts over a 4-hour duration, or you could deliver 10 megawatts over 8 hours, right? It's pretty simple in terms of the math, in terms of how much you can provide. Is my understanding correct?
Pretty much, yeah. And I think, you know, one of the things with our energy park model is that we have the additional issue of making sure that we can provide the minimum amount of emergency power required to both schools at any time. So on the energy park, we can't fully discharge the battery. We need to maintain a minimum level of charge of 8%, so that at any given time, if at the worst possible moment the school's lost power, the battery would be there for them. So there's been a calculation to determine what we need for a minimum charge level. And that's when the generator that you saw in that picture would have to kick in if we were fully discharged and we had to run and provide backup. That's what we would use. So that's why it was designed that way. But overall, you're pretty accurate in terms of the way you're describing it. So we will run less output for a longer period of time, or more output for a shorter period of time.
Great, thank you. So I've got a couple more questions, but I think there's one question from the audience that is sort of particularly timely here. So let's put that right to you guys right now, which I think I'll start with you, Pete, and Abby. Feel free to jump in if you have more to add. But the question is, if you could explain more, Pete, about how your battery projects, I guess, in the future, act as a capacity resource in the New England grid, and how, to what degree you were qualified as a capacity resource.
So we're not in that we're not in the capacity market. So we're on the other side of the meter. So we're a local resource. But again, ISO New England monitors all those behind the meter resources all throughout New England. So they're measuring how much we are available as well. So in the past 2 years, ISO New England has made a move forward to look at not only the capacity resources that bid into the market, all those resources that are on the other side of the meter like ours. And from our perspective, we're looking at it from a Wakefield perspective to make sure we manage our capacity costs and our transmission costs. So if to the extent that we can run these resources at times when the peaks are hitting, it saves us money in terms of our transmission charges and our capacity charges.
Gotcha. Okay. Abby, do you do you want to jump in there,
Yeah,
please?
so talking about the big grid that, ISO New England, as Pete mentioned, they're starting to pay more attention to the smaller systems. But for the grid scale systems, batteries can register and be paid into a forward capacity market. So essentially you're saying like you will be available during critical peak periods, like I mentioned before, which, helps ensure that reliability. And so when demand surges, especially during, summer, winter peaks and the daily peaks I mentioned, early in the morning and at dusk, kind of early in the evening, the stored energy is released to meet the need. And then when, if you're a capacity resource, if there's something that happens on the grid, you'll be discharged to, if a large generator trips offline, you'll be discharged to kind of make up for that. So, that's how ISO New England and how others would, operate that as a capacity resource.
Great. Thank you, Abby. So you've raised a couple times now sort of the peak, delivering on the peak, and certainly in Massachusetts and states across New England and beyond, energy affordability is a paramount concern and discussion at this point. Can you explain a little bit more about how storage, bringing a resource into the grid to meet demand at that peak can help with affordability, given the high level of cost of power at the peak in peak periods?
Yeah, so when demand is high, prices are high. But renewables have zero cost fuel, which makes, as they're have output, those prices are pretty cheap. So because batteries can draw from those cheap resources when they're at their peak output, store it, and then discharge when demand is high, prices would generally be higher. And then that's the point where, like, if the sun isn't shining, the wind isn't blowing, you're going to have to turn on those more expensive units to run. And so instead, batteries will use all of that stored energy that they got from the cheap renewables. And instead of turning on the more expensive thermal generation, you're just going to discharge the energy you stored earlier. And, by the way, batteries can do the same thing for natural gas. And, I think another piece is providing that congestion relief I mentioned earlier. I think outside of the real-time context, that kind of does help defer the need to build new transmission lines and, expensive grid upgrades. That I think can also be particularly impactful in New England, where we do see a lot of densely populated areas and such, where, building large scale infrastructure can sometimes be a challenge. So I think in real time, it is just utilizing those cheap electrons and saving them for, when they're most needed, which helps bring down bills, helping with gas electric coordination, especially crucial in the winter when we do see that solar output decrease and the use of natural gas ramp up. And then, kind of in the longer term, providing that, and in the immediate term, providing that congestion relief.
Great. Yeah, I think there was an analysis by the Commonwealth that said in Massachusetts, I may have this number a little off, but I think it was 40% of the cost of the energy supply that ratepayers pay for come during the peak periods, right? Which are, a relatively small number of hours, but they're the most expensive. So if we can make those hours cheaper, then rates come down. So that's one of the two ways which storage can help with affordability. Let's want to toss the ball to Nick here for a second with a question that has come in from the audience. How do storage developers generally work with local public safety officials when proposing and permitting and trying to get a project going?
Yeah, just like voting early and often. As soon as you have committed to putting an energy storage project in a location, go ahead and go meet with the fire department, go meet with elected officials, go meet with the landowners. You don't necessarily need to roll out the red carpet and bring a big banner, but once you have an understanding of where the system is going to go meet with the fire service immediately, as well as elected officials. Let them know you want to come into town, see what questions and concerns they have, and start working to educate them. Massachusetts especially is lucky. There has been a lot of energy storage deployed around the state. The fire service communicates well amongst themselves. There are definitely still pockets where they don't have experience with energy storage and the guys are asking questions. But there are a lot of departments there too that have had batteries for several years and have had positive experience with them. ESRG has been fortunate and privileged to have worked with a lot of departments around the state. We've got a number of our colleagues are in Massachusetts or near Massachusetts and have worked to permit projects as well as train the fire service. So engage with those guys, engage with your elected officials and landowners. Once they're on board with the project, consider having town hall meetings. We've had tremendous success with those. 4 or 5 years ago, they weren't a necessity necessarily. It was a nice to have. They've become much more common with deployment. When there's questions from the community, they go a long way with making everybody comfortable with the projects. ESRG does a battery 101 for project stakeholders as well, where we can educate folks, get on those myths and realities and talk about what mitigation measures are in place, what code requirements are in place, what fire service response options exist to manage incidents should they occur. So it really comes down to education and engagement and started at the beginning. I would caveat that though, with the fire department is not a design firm. Don't go to them with an inkling of what you want to do and then expect them to give you all the answers. The codes exist. There's a lot of entities you can work with as consultants and as construction companies and engineering firms that will go ahead and design the system. They know the local codes and requirements. So put it together, come to them with, hey, here's what we want to do. Does this look good? But, don't necessarily leave the ball in their court. Have a plan, understand the technology, be able to educate them on it.
Good answer. Thank you, Nick. So sticking on this topic of siting and sort of community acceptance, the question came in for you, Pete, which is how Wakefield, how did your community react to the siting of the batteries that you have? Were there concerns?
Sure. So the first battery was installed within a substation yard, so there was minimal impact with the community discussion other than local police, fire, and public safety because it was within our yard, basically. But that experience helped us with the next project. The next project, we needed to have about an acre of land that was town-owned land to site the energy park on. And there were some concerns about that. I think overall the community felt that the benefits outweighed the loss of an acre of land. However, as a municipal electric department, we were able to do some trade-offs. We were able to retire an old 4 kV substation, and we gave that land. We created a park and gave that land back to the town. And we also did a few other things in terms of the fact that we had to take down some vegetation. So we reforested an area of town as well. So that we work closely with the town, but overall the economic benefits and the supply benefits to the town outweighed the fact that we did need a piece of land. But overall, I think when we proposed the energy park to the town, there was universal support from all the boards, the select board or the town council, the planning board, the FinCom, school committee all came out in force to support it.
Terrific. Thank you. So I'm going to stick with questions that have come in the Q&A function. But again, remind folks there's still some opportunity to get your question in. So please do so if you've got one. Here's a question that I think is referencing battery storage sort of in the system writ large, sort of the grid. I hope I'm not misreading this, and it's intended to be just focused on a single deployment of batteries. What are the current limits to battery storage capacity, and what could accelerate more capacity, or what is the limiting factor on growth in capacity? So again, I think that's referencing sort of in the system as a whole, not just in one facility, because they're not other than interconnection and limitations that ISO has on for reliability purposes on all sources of power, transmission lines, nuclear power plants. There's no, I think, real theoretical upper limit. So, Abby, any thoughts about, kind of how much battery storage could be built out in a system, in a state, or within an ISO?
I think, I'm not sure that there's, really a technical limit in theory to how much battery storage can be built out. But, a lot of what we use battery storage for, as I said before, it does also work with natural gas. But, on the kind of renewable side, I think as you start to see a lot of saturation of grid scale battery storage in a given market, it kind of all tends to pile up on the same amount of risk hours. And so I think, as you see a lot of saturation in a given market, I think at that point, it would be hard to integrate more, maybe coming, from a technical perspective. So I think that that's, one limitation if the question is being directed in that way. But if we're, talking about barriers to kind of expanding deployment of battery storage, I would have a different answer for that.
Well, why don't we ask that question too? Because actually that was going to be one of my questions anyway. So
yeah.
Yeah.
No.
Can
Yeah.
you
So,
touch on that?
for sure. So I think, locally, and I think Pete would probably have more to say on like the local side. Municipalities might have conflicting or overly restrictive zoning rules for battery storage projects. There are some inconsistent state level regulations regarding permitting, because remember, like you're part of a grid operator, you're part of a, wholesale region. And so, you could be in the same grid operator region, but depending on the state you're located in, your process for interconnecting the grid can look pretty different. And so the generator interconnection process itself, the process of actually connecting a project to the larger electricity grid, has consistent bottlenecks across the country, including in New England. To interconnect, you have to go through a series of studies to measure your impact on the broader system. And so there have been and continue to be significant delays in performing these studies. FERC Order 2023, which the grid operators have to follow, attempts to address a lot of these issues by really streamlining those study processes and kind of holding both parties on the developer side and on the transmission owner side accountable for pushing things through in a timely manner. And so, as you're going through the process of interconnecting to the grid and getting your project built, there's different factors and authorities that you have to deal with when it comes to that. And so there's a lot of room for things to not turn out as ideally. So I'll stop there and see if you want me to. You have a follow-up question.
From our side, since we're on the other side of the meter, our physical restriction is the load that's on our system. Obviously, we can't produce more out of the battery than is being used by the system, or what we're generating will actually flow back onto the transmission grid and create different issues. So we have to make sure that we're attaching the batteries to places that, you know, the output of the battery doesn't exceed the load on the circuit at that time.
Well,
Great.
just one thing to add, I know I'm the safety guy, but I've been in batteries a long time, and I remember hearing 3 or 4 years ago, talk of market saturation in California, market saturation in Texas, and rising electricity rates, decreasing battery rates, improved performance out of batteries, increased density out of batteries. All these have contributed, I think, to increase the amount of battery that could be deployed on a system. Obviously, the market has to be there. The rules have to adapt quick enough. The interconnection process has to approve things quick enough. But I think the demand for storage, whether it's in front of the meter, behind the meter, is significant. And as we look to reindustrialize the United States, there's tremendous benefit to behind the meter batteries as well as we roll out electric vehicle charging, through municipalities and other dense areas. I think we're going to see storage, not just ubiquitous in our pockets and our homes, but stationary storage in a lot of different scales everywhere.
Yeah, good point.
Yeah,
I was gonna-
I just to tag what Nick said in terms of, that's a perfect example, the charging. You know, if you have people passing through your town and they're stopping to charge a vehicle at the peak time, our costs go up significantly because, so we have to make sure that we partner our battery with, EV charging rates and things like that, so that all the systems work together. But having a battery helps obviously offset that because of the fact that we're minimizing our impact on the grid overall.
So if folks are on the highway traveling through Wakefield, do you want them to pull off and charge up their car, Pete?
They can now.
Okay. All right. Everybody's heard it here. That's great. I was going to save this question maybe for the last, but since we're sort of in it, let's stay in it, which is the question is just given the market, the policies and everything in Massachusetts, how much more development of battery storage projects are expected in the next several years. And as folks think about that a second, I will first just give a broad answer, which is to say, in my many years of energy project development, one of the first things you learn is that the projects that request interconnection from ISO New England and get in the queue, the survival rate, the success rate of all those projects that go in is really quite dismal. Your batting average is certainly not 300, well below a Hall of Fame level if you're a baseball player. Typically, the percentage of projects, and I'm talking about all types of projects, generation projects, fossil, renewable, it is under a quarter of 25% of the projects that get in the queue. I forget the specific number, but the attrition level is very, very high, and for all sorts of reasons. And storage, like everything else, is not immune to the challenges of developing energy projects. So whatever the number is out there in the world for any type of resource, you typically see a pretty small percentage actually end up on in service eventuch So with that positive note, any thoughts anybody else wants to chime in about how much additional battery development there might be in Massachusetts in the near future?
I'll chime in and then I'll give it to Pete. I know Massachusetts does have, a state goal of, I think, about 5,000 megawatts by 2030. As you so poignantly pointed out, Dave, that also just very much, again, depends on the interconnection process and how quickly that is able to move along. And, you can have goals, but getting them through the queue and actually online is a different story. And so I think, I I hope that it can reach that amount by 2030. I don't actually have the exact number on how many projects are in the queue right now. But I think with reforms like Order 2023 and such, that should improve the rate at which those projects, and all the others in the queue are able to come online. So I guess I don't have an exact number. But as Dave pointed out, it may not be as high as, the state goals would have it or that we'd like.
On the municipal side, MWEC embarked on a project that we're participating in for the Energy Parks battery side, where they went out to bid for this standard 5 megawatt, 15 megawatt hour battery, and a company bid on that and won that project. And actually 12 munis are installing these batteries, and I think they're up to 8 or 10 installed right now. And we're actually considering an additional one. So by the time it's all over, we may be up to about 15 of these 5 megawatt, 15 megawatt hour projects spread throughout the state. And so I think, that's kind of, that model is built around a shared savings model between us and a company called LightShift, which is the one who's creates this shared savings model. So that's a form of a project that we may see, gain in strength over time. From a municipal perspective, we had very little capital outlay, and we share the savings that's generated with LightShift. So that's a model that's being considered, and I know there's other companies that are doing similar shared savings type models, and I think that's going to encourage even more use of batteries on a distributed basis.
Great, thank you. So a couple final questions, and we'll head toward the wrap up. First, are there any alternatives to using rare earth minerals that are currently needed for at least lithium ion batteries? And before one of our panelists hopefully jumps in on that, I will note, as probably many folks are aware, there's a lot of research and development going on a wide range of storage technologies. Lithium ion, I think, remains and probably will remain, at least for a little while, the dominant technology in this space because of its performance and economics. But we may be talking about a very different type of battery storage or storage technology, maybe not even battery, but some type of different storage technologies, in years to come. But rare earth minerals, anybody? We're not really battery manufacturers here on the call, but maybe somebody has some insight. Nick, do you have a sense?
Yeah, so the engineer in me is going to be a little pedantic here. There aren't really rare earth minerals like neodymium or anything like that in batteries. You have two families of technology with lithium ion batteries. You have the lithium metal oxides, so nickel, manganese, cobalt, nickel, manganese, aluminum, nickel, cobalt, aluminum. Those are typically a little higher energy and power density. Those make up most of your automotive batteries. You do see those in grid scale applications, but there's really been a huge push in the last few years to move to one of the other families of chemistry, which is lithium iron phosphate. There are some sourcing issues with cobalt and manganese. They're not technically rare earths, but they do come from places that politically are tenuous for a few different reasons. LFP really solves that problem. Iron and phosphate are much more common everywhere. Less politically tenuous. The rest of the composition of the battery is really, from that point, just plastics, copper, aluminum, and carbon. So LFP will definitely help, but for the most part, once we start to close the loop on recycling in the next 5 or 10 years, I think a lot of those issues, regardless of chemistry, will go away. And I will say, we don't talk about the recycling space a lot, but DOE has invested in it heavily over the last 8 or 10 years. There's been some successes and some losers, to be honest, but that industry is coming along nicely, and battery second use is developing well as well. So my hope is that in a couple of years, I think this feeds into the next question, we'll see the the life cycle of a battery kind of start to close like lead acid. You know, lead acid batteries are one of the great recycling success stories in the world. Over 99% recycling of lead acid batteries, and I think we'll see a similar success rate with lithium ion.
Thank you, Nick. And you've actually sort of led us perfectly into the last question, and that is really what the design life of the systems are, the battery systems are today. You know, batteries degrade over time, and so at what point do you typically have to think about replacing them?
Yeah, the design life for the systems now is 10 to 15 years. Most of the projects that are built are actually the capacity that's permitted is greater than what actually goes in initially, either because they're leaving open racks or they're leaving space to install additional cabinets at a later time. So augmentation of the system is planned from the get-go. And usually the expectation, I think, is, you know, you'll have a 10 to 15 to maybe 20% decrease in capacity over the life of the project that'll need to be supplemented. Um, you know, we'll see how that plays out. I'm sure Peter can speak to that more. I think there's some systems out there now that are probably going to last way past 20 years, but there's a lot of systems out there now that are getting beat up hard that are not going to come anywhere near 20 years, to be honest with you, or even 10 or 15. We also see too, with some of the systems that are out there, balancing with the battery becomes problematic. So you're not really losing life in the battery, but you kind of have to take it out of service for a while to kind of get everything back into whack, so to speak. But I will say the manufacturers that we've worked with have gotten significantly better at managing this over the last few years. And I'm actually pleasantly surprised how quickly some of the control issues have been solved to keep these batteries usable for a lot longer than we saw even 5 years ago.
I think, as Nick was saying before, the design and the fact that they're so modular now, looking at individual cells, can help keep the overall project going longer because you're more closely monitoring each individual cell. Excuse me, the design of our shared savings model is that, again, if the battery degrades over time, both of us lose money. So there's an incentive on both sides to make sure we're monitoring closely and replacing cells if they're failing faster than the average of the site.
And generally, from a safety perspective, good operating practice to extend the life of the system is also a good safety practice in terms of understanding the conditions. So it's, you know, this isn't an industry where cutting corners and thus creating a safety issue may make you more money long term. It's actually not. The incentive is to both preserve the life of the system and be safer.
That's a great place to leave it and a great final note. And I want to thank the three of you for your insights and time tonight, and thank everybody who tuned in, and hand it back over to Nathan.
Thank you, Dave. And please join me in thanking our amazing panelists for this amazing conversation this evening. I know that weren't able to get to every question and touch on every topic. If you'd like to hear more from Renew on this material, please feel free to reach out, as we'd be happy to continue this dialogue in the future. Thank you so much for attending this evening. Have a great night and have a happy holiday.
Thank you.